All right, so I was saying that this is just an example of an arrangement that I have given you. We can have a different arrangement where the atoms are arranged like this. So this can be another different arrangement of atoms inside what? Inside a solid material, which we can also call a what? A crystal structure. Okay? So it's not always that the atoms will be arranged in this order. Maybe they can be arranged like this, where we can see that there are some spaces here. So we can also call this what? A crystal structure. So there are various arrangements of atoms inside the solid materials. There are various arrangements of atoms inside solid materials that give us different what? Crystal structures. So in EG 244, we mainly focus on four types of arrangement, and with emphasis on three. So we focus on four, but we put more emphasis on three arrangements. So we focus on the SC, we focus on the BCC and the FCC. And we also talk about the HCP. So I'll tell you what this means, don't worry. But the arrangements that we have of atoms, the arrangements that we have of atoms inside a solid material are about 7, if I'm not mistaken. They are about 7. So on those 7, we only focus on what? 4. Okay? With much emphasis on 3. The 3. Okay. So another thing that you should know about these crystal structures is that they have a repeating unit. Since we said that they are highly ordered and repeating, they have to have a repeating unit time. Like for example, ichibumbain, a war. Would think of the repeating unit to be the brick sign. So you have the brick, another brick, another brick, another brick, another brick. So the brick is doing what? It's the repeating unit of the what? Of the wall. So even crystal structures have got repeating what? Units. The units that repeat and repeat and repeat to form what? A crystal structure. So from this example, bricks, we're saying that when you put a brick, you lay another brick, you lay another brick, you keep on repeating that process. What you form is what we are calling what? A wall. Fine. So when you repeat the repeating unit of a crystal structure, you repeat it, what you form is a crystal structure. Okay, so what I mean to say is that my crystal structures, they are made up of repeating units, and these repeating units, we call them unit cells. Okay, so we call them unit cells. Unit cells, when you get one unit cell. So assuming that this was a unit cell, right? You get one unit cell, you get another unit cell, you get another unit cell, another unit cell, another unit cell, another unit cell. You are forming what you are calling what? A crystal structure. Have I lost anyone? Okay. So let's say we had a crystal structure which had this arrangement of atoms. Of this one, this one, this one here, this one. Okay. So again, Munshum, you've got this same arrangement. I don't want to mess up the arrangement. I don't know if you can see the pattern here. Can you see it? So these are atoms. This is a solid material. Right? Maybe this can be iron. And the atoms inside iron are arranged like this. Right? You see this. This is the arrangement of atoms inside iron. So we can see that there is a repeating pattern here inside this solid material. So this arrangement of atoms is being constructed by what we are calling what? A unit cell. That wakabula ka unit cell kamoto wakabika. If you get one ka unit cell, we put it here, we get another unit cell. So if we get one unit cell, you put it here, you get another unit cell, you put it here, you get another unit cell, 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 another one. We are forming what? This. Right. So let's try to identify the unit cell here. That is the unit cell that is here, that is forming this solid material. So ka unit cell na kena kabafe kwat. Do we understand? Does everyone understand Bemba here? Not everyone. Hey guys, you've been here for how many years now? And you're saying you don't understand? Eh? 9 months. You've been here. No. Oh, it's 9 months. But still, 9 months is enough for you to learn how to speak Bemba. But anyway. People want MATLAB. All right. So we need to identify the unit cell here. The unit cell is a box, in short. Okay, first finish up with the MATLAB, but then we continue. Steve, kweta ma flash yan. One. I think you can be getting one at a time. Okay, so you'll be getting one at a time. When it's done, Aisa send Naimbi. Okay, so I was saying that we need to identify the unit cell here in the arrangement of atoms, right? The repeating unit. But I think I remember you. Were you not there? Ah. Okay. So I was saying that the unit cell itself as well appears like a box, right? It appears like a box. It's actually 3D, but we're going to we're going to locate it as a 2D, as a 2D, as a 2D unit cell. So the unit cell yambila pa center ya atom I. So from this center of this atom, the center of the next atom, center of the other atom like this. Okay, alright. Now this nani kanye itairepanga tairi symmetrical arrangement in Chirembe. It should be like this. Okay. So I was saying that the unit cell here is this one. Namukamonaka. This is the unit cell. Akaso. Nganaka bulaka. I repeat it again here. You see, ka? I get it again. I repeat it. Center, center. Are you seeing the unit cell? So Ngana, if I were to get this and write it on its own, it would appear like this. You've seen, ka? If I were to write this on its own, it would appear like that. And when I get that, I repeat it, I repeat it, I repeat it again, I repeat it. Even down here, I repeat it, I repeat it, I repeat it. What I'm getting is what? This. I don't know if you guys can see that. Okay. So that's the unit cell. The repeating factor of a crystal structure. So maybe I draw a different crystal structure rather than this one. The simplest arrangement that we have. The simplest arrangement that we have of atoms inside a 3D, inside a solid material. Sorry. Inside a solid material is this one, eh? This is the simplest arrangement that we have. So if I were to say, let me find the unit cell of this arrangement, the unit cell would be this one. So if I get this one, I repeat it again. Even Munshumu, I repeat it. Are you seeing that? Are you seeing that? So if I were to write it on its own, Tkamone Kasoka unit cell, it can look like this. Aye. Yeah. So if I get this, I repeat it, I repeat it, I repeat it multiple times, I guess I get this arrangement of what? Atoms. So I don't know, guys, if you are following me. Are you following me? So this is an arrangement. This is an arrangement of what? Atoms inside a solid material. This is one arrangement. This is another arrangement. Aye. So this arrangement of atoms will be called by a different name. This arrangement will be called by what? A different name. Okay? So I told you that this one is the simplest. This one is called simple cubic crystal structure. this one. And we've got this other one as well. This other one, this looks like it looks like BCC, but anyway, we'll confirm if it's either BCC or FCC. But this one is CS, simple cubic. All right. So remember, there's an element where I said that crystal structures are highly ordered. We can see the order, right? Repeating, we can see that it is what? Repeating. You can see that. And again, I said 3D arrangement of atoms. But what I'm showing you here is what? 2D. You can see that what I'm showing you is 2D. Right? So if we say that it is 3D, this has to be represented in 3 dimensions. So what I mean is that what you're seeing here are the atoms in front. Even the atoms behind this have got what? The same arrangement. Okay? What can I use to give an example of this? Let me try to get this. Okay, so what I'm showing you are the atoms in front, right? So these are the atoms in front. What I'm showing you. So even on these atoms in front, there are atoms where? Behind. Even though behind those atoms that are behind, there are more atoms that are what? Behind, forming a 3D what? A 3D structure. Okay. So what I mean to say is this arrangement can be represented in 3D. So if this was so if this was my 3D what? My 3D material or solid. We can tell that it has got these atoms that are where? That are in front. Even behind these atoms there, atoms, right? Queen of so I think you've picked what I'm trying to say. I think you've understood what I'm trying to say. So, if we are saying that the arrangement is 3-dimensional, it means that even the unit cell can be represented 3-dimensionally. Okay. So I'll start with simple cubic, which is this arrangement. Ikwatama atoms are aligned like this. So the 2D presentation, I've already shown you that it looks like this, and this is 2D. What if I wanted to write this in 3 dimensions? So if I wanted to write that unit cell in 3 dimensions, it would look something like this. It would be quite a box sign. Then but I think you can refer to the images that I've sent in the group. Can you kindly refer to the images that I've sent in the group? Okay, this is hard to draw, but naesha kala moneka so. Can you refer to have you seen the images that I've sent in the group? Nam kamona kale moneka so. Apart at simple cubic. You've seen it, ka? Yes. So What is happening? These things that are on the corners here are these atoms. But these atoms are being what? Cut. Because if you can see, this box is not encompassing the entire atom. It's just getting what? A portion of an atom. And I should have mentioned this. In crystal structures, we assume that atoms are solid spheres. So if I'm where you say atoms have got electrons and whatever, you don't consider that. You just consider atoms as a solid sphere, like a bow. So that bow is being cut. You cut it, you get this. So that is what we are getting for, this is for simple cubic. The front presentation is what you're seeing here. Then again, there is the what? The 3D representation. Okay. So I think you can see it if we do it like that. So this is the unit cell for what? Simple cubic. Are we together? Yeah, so this is the unit cell for simple cubic. Or sometimes you may find that it is not represented like this. So sometimes I don't know if it's the drawing or I don't know what causes that. So you find that sometimes it may be represented like this. You've got your atom, and behind these two atoms, there are atoms behind, right? Behind these two atoms, there are other atoms behind. So sometimes you may find that it is represented like this. Okay? So you've got this atom, which is the one here. You've got this other one, which is the one here. You've got this one, it's the one here. This atom, Tylemonica here, it's being covered. Don't know if you can see that. Can you see that? So it's being covered, Tylemonica, this atom. But we know that this one here is the one upper. This one here is the one here. This one is the one here. This other one is the one. We see that, ka? Yeah. So you might find that sometimes it may be represented like this. Even you guys, as you be drawing, you may not write like this. You may write it like that. But me, I don't like this presentation. The reason why I don't like this presentation is because this looks like these atoms are not touching each other. If you look at the alignment that I gave you, the atoms were doing what? Touching each other. Even here, you can tell that these are touching. But when I write it like this, you find that it's looking like they are not doing what? They are not touching. Okay, can we see that? All right. So the next thing that you need to know about this arrangement, this crystal structure, or this unit cell, next thing that we need to know is how to calculate the volume. How to calculate the volume of this unit cell. So I said this is the simple cubic. How can you calculate the volume of the simple cubic? I think I will not go over how you calculate the volume of the simple cubic because that's what we covered last time. I'll just give you the formula. Just give you the formula. You may go on how to calculate the volume of this at your own time. But the formula for volume is equal to, but I may just have to calculate it because I've forgotten myself. I've forgotten. Okay, let me just quickly go over how you calculate the volume for this. You need to know how to calculate the volume for this. And how to calculate the volume for the simple cubic is derived from the fact that this is a what? A cube. And we know that the volume for a cube is what? If this side is A, even this side would be what? Even this side would be A. So the volume would be what? A to the power what? A to the power 3. Okay. So if I were to represent it as a 2D, it would look like this, eh? Like a unit cell. If I just represented it in 2D, now send up of a side frame, it would look like that, eh? And I'm saying that the distance from here to here is A. I want to calculate the volume. So you find that we are saying that the volume is equal to A to the power what? A to the power 3. But we don't know what A is. I we don't know what A is. What do we know? We know what the volume of a sphere is, or we know what the radius of an atom is. If we're talking about if we're talking about the iron atom, for example, the copper atom, we can tell what the radius of a copper atom is. You can tell what the radius of an iron atom is. So I'm saying we don't know what A is, but we know that what we are talking about is that these are atoms, right? They are saying that these are atoms. If we say that these are atoms, and we are assuming the atoms to be solid spheres, the distance from the center of the atom to the to the outermost part, that distance we will call it what? R, which is the radius of the what? Of the atom. Are we following? Okay. So the distance from the center to the outside of the atom is what? Is the R, which is the radius of what? The radius of this atom. Okay. So I don't know if you can see this. We need to find a relationship between A and R. We need to find a relationship between A and R. So the relationship between A and R is that I don't know if you guys can see that the distance from here to here is R. Can you see that? Jonathan, where is Jonathan? Do you see that? Jonathan, you were there last time. Yeah. So the distance from here to here is what? Is R. So Kairi, if I were to complete this, it would be a full what? A full atom, right? So this is the center. So saying that this distance is R, it is the radius. So if this distance is R, even this other distance is what? Even this other distance is R. So we can say that this total distance here is what? 2R. But again, we are saying that this is A. Okay? So it's 2R again, it's A. So in short, what we are saying that is that A is equal to what? 2R. Are we safe? Yeah. So since this is a cube, and we can see that this side is identical to this side, we can say that even uku, we have 2 what? 2R. Okay? So if I come back to my 3D, if I come back to my 3D unit cell here, I would say this is 2R, this is 2R, even this one is 2 what? 2R, right? The volume in that case would be V is equal to A to the power 3, but we know that A is equal to 2R, so the volume will be equal to 2R to the power what? To the power 3. This would give us what? 8R to the power 3. Have I lost someone? Question? Guys, mune mumfisha olusofu mulemu ngikafu. Echingafi. Guys, we kere kulia plastic. Bro, are we together? Lost. Ah, okay, you catch up. Okay, ushadire pesa. Hmm? Fiance. Hmm? Everything. Eh. Guys, anyone knows njebenyopo mushadire pa kusanga volume up so that we can quickly clear out that misunderstanding and try to move on. Where are we behind? Okay, you are not telling me, so I think we should continue. Since you are not telling me, so this is the volume for what? This is the volume for simple cubic. This is the volume. I will introduce something new that I didn't talk about the last time. I'll introduce something that I didn't talk about the last time I didn't talk about the atomic packing factor of a unit cell. So I'll talk about the atomic packing factor. Okay, so each unit cell that we are going to look at has got an atomic packing factor. So each unit cell that we talk about has got an atomic packing factor. In our case here, we are talking about the simple cubic. The simple cubic has got an atomic packing factor. So someone may ask, what is an atomic packing factor? An atomic packing factor is just the amount of space that the atoms have occupied inside the unit cell. Okay? Amount of space that the atoms have occupied inside the unit cell. So if we think of a unit cell as a box, how much space have the atoms occupied inside this box? Okay, so if we think of this as a box, and inside this box we are putting what? Atoms. How much space are the atoms taking inside the box? So we determine that by the atomic packing factor. Or in short, we can call it the APF. So for you to find, for you to determine the atomic packing factor, first you need to determine how many atoms are inside this unit cell, inside this box. Anyone to take a guess? How many atoms? So, okay, how many atoms are in there? Diodone is saying one. How many atoms are in this box? He's saying 8. Yes. 7. Okay, anyone else? Yes. 1. How many atoms are inside that box? Okay. About under 8, in technical reason. Just give me a simple reason why we have said 8. Yes. Okay, so he's saying that this box, if we drew it like this, we see that it has what? It has 8 corners, right? And on each corner there is what? An atom. On each corner there is an atom. Hence, this has got what? 8 atoms. That's what he's saying. Who said that 1? Give me the reason. Okay, we start with you first. Okay, Dieudonné.
It's being shared by other unit cells. So if you look at that first diagram, close to when negatively half, it's not a complete atom, meaning it's just 1/8 of the full atom. So by the fact of most stones, it maybe gives us one atom.
That makes sense, ka? Yeah. Okay. Here's what these guys have said. The first one said that since each corner has got what? 8 atoms. Since each corner has got 1 atom, and we've got 8 corners, hence there are 8 atoms. But remember that this is not a complete atom. It's not a complete atom. Even here, it's not complete. Even here, it's not complete. It's not complete. It's not complete. It's being chopped off like this. So if we look at this, it's not complete, eh? So it was cut like this, 1. Cut like this again, 2. Again cut like this. It was cut how many times, dear? This atom, it's been shared. Because if we write like this and we say this is the unit cell, we see that we are cutting it how many times up? If we consider we've cut them how many times? 1, 2, 3, 4, right? We've cut 4 times. But again, this is in 2D. If we present it in 3D, we are cutting this again how many times? 4 times. So I don't know, you can just gun that one. Just know that the atoms that are at the corner are being cut how many times? Is it 4 times or 8 times? 8 times. If we represent it in 2D, we see that they have been cut forward 4 times. But if we present it in 3D, they have been cut how many times? 8 times. Pa. This is it was a hard concept to understand. But go get a tomato and try to cut it. But I think The only conclusion that you guys need to make is that atoms, the atoms that are at the corner are not complete atoms. They are 1 over 8. They are not complete atoms. They are what? 1 over 8. So this one is 1 over 8 of an atom. Hii pa corner. Even this other one is 1 over 8 of an atom. Even this one is 1 over 8 of an atom. Aye. Do we see that? Yes. So if we understand what I'm saying, I think this would be easier to represent if I consider this one. Right? So if I were to consider this one, I'm saying this one is 1 over 8. Right? This one here is 1 over 8. This one 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 is 1 over 8. 1 over 8. 1 over 8. 1 over 8. We see, ka? So how many are these corner atoms? The corner atoms are how many? 8. So the corner atoms are 8. And we are saying that they are not complete atoms. They are what? 1 over 8. So if we were to add them, we say 1 over 8 plus 1 over 8, 8 times. The answer that we get is what? 1. So you can just simply say 8 times 1 over 8 to give you what? 1. So that means that this box just has what? 1 atom. If we were to add them, are we together? Sometimes abali ukuba chitaku understand abali kunuma kulya katwishifire chitika. You look confused. You understanding? Okay. But you don't have to lie. Okay. That was a joke. All right. So this just has what? It just has 1 atom. So this entire box here, this entire unit cell just has 1 atom. So we have determined that. So what we are trying to find out here is the atomic packing factor. And I said that the atomic packing factor is the amount of space that the atoms occupy inside the what? The unit cell. So we have determined that inside this unit cell there is just what? 1 atom. How much space has that one atom occupied inside this unit cell? How much space has that 1 atom taken? So in order for us to do that, we calculate the atomic packing factor by determining the volume of the atoms that are inside the unit cell. Right? So volume atom or atoms. So we take the volume of the atoms that are inside the unit cell and we divide that by the volume of the what? The unit cell for us to determine what? The atomic packing factor. Okay, so we need to calculate the volume of the what? The unit cell and also the volume of the atoms. So we have already determined the number of atoms that are where? Inside the simple cubic. Simple cubic has got how many atoms? It just has 1. So we need to find the volume of this 1 atom. I told you that we are assuming that atoms are 3D what? Are solid spheres, sorry. We said that the atoms are solid spheres. They are like balls. I was like, Nakshama I was like, that came out wrong. Okay, baller, guys. Okay. Yeah. So yeah, the atoms are solid spheres, right? And we know how we can find the volume of a sphere. What is the volume of a sphere? The volume of a sphere is, Jonathan, what is the volume of a sphere? 4 over 3 pi r what? Wala ba kakene, why you swap them in the test. Okay, anyway. So we're saying that the volume of a sphere is this one, right? And we are assuming that atoms are what? Are spheres. So in short, this is the volume of the what? The atom, of one atom. Right? So here we are going to say that the volume, since we only have one atom, it's just going to be 4 over 3 pi r to the power what? 3. If this unit cell had two atoms, we would have taken the volume of what? Two atoms. So we would have said 2 times I. Okay. So, but it's just one, so we just take 1 over the volume of the unit cell. What is the volume of this unit cell? We found that it is 8r to the power what? 3. So the volume of this unit cell is 8r to the power 3. We're trying to compute the atomic packing factor. Okay. So this would give us what? The r to the power 3 and the r to the power 3 would cancel, right? We would remain with 4 pi over 24, which is pi over what? Pi over 6. It's pi over 6. Okay, so that pi over 6 should give you 0.5. Is it 0.53 or 0.51? I can't remember. Can you punch this? 0.552 what? Since you conkapo. 3, 5. Okay. So usually we find the atomic packing factor in percentages, right? So if we were finding in percentage, we would have multiplied times 100, right? Times 100. Even this one times what? 100. So it would have given us 50 what? 52.35%. But guys, they 51 yard of me. Okay, I'll take what you've given me. 52.35%. So what that means is that the atoms that are in this unit cell have only occupied 52.35% of the unit cell. Do you understand that? That's the amount of space that this atom or this atom has what? Taken inside this unit cell. Yeah. So the other space is just left like that. As you can see here, there are gaps. There's nothing. So this unit cell has only taken what? 52.35. This atom has only taken 52.35% of the unit cell. Any questions so far? Yes, Wendy. Oh, Wendy. Muhau. Wow. Okay. Yeah. Here, I said times 100. No, it doesn't have a unit. So are we clear? That's so. If we have all understood that, that's all about That's all about the simple cubic type of crystal structure. So, guys, this is not what we were supposed to do today. We were supposed to, by now, we would have answered a past paper question. But I find that the majority of you were not there last time. So I had to repeat some of the things that I talked about. Okay. So that was the simple cubic. I want us to look at a different crystal structure that we call the FCC. The FCC just stands for face-centered cubic. And if we were to represent it in a 2D presentation, it would be that one that I was drawing. If you remember it, that one that looked like this. This would be the 2D for an FCC. So its unit cell then would be this one. Okay, its unit cell would be this. It would look something like this. Oh no. Okay. So make sure these atoms are not touching, because in actual sense they don't touch. Okay, so that would be that would be the FCC. So make sure when you're drawing this, the atoms are not doing what? They are not touching. Okay? It's like this one is independent. You've got the center atom. It's like this. They are not touching. These ones are not touching, but these are touching with the center atom. Okay, so that's the 2D representation of an FCC. The 3D representation, you refer to the one that has been sent in the group. Please, mumfa obunanganya okuya mukulolesha eri mu group ilolesha anymore, because me when I draw it will to look confusing to you. think this is as far as my art skills can go. Have you seen the one that is in the group? Have we seen the one that is in the group? Okay. So how that one is that, okay, you know what I'm showing you here? It's like we had spheres. We had spheres all over, like we cut them in the middle. To get this. So if I were to write it in that other representation that I don't like, we would have our unit cell. We would have our unit cell. We would have those corner atoms. Always you have those corner atoms. And even for this one, it's the same. They are 1/8. They are being cut into 8 smaller parts. So you've got your 8 corner atoms like that. But there is this atom that you're seeing here. There is this atom that you're seeing here. So what this atom is that it's an atom that is at the center of the face. So this is the face. So it is at the center. So that's why we are saying face-centered Cupid. But this atom that is here, it is not a complete atom. Okay? It is not a complete atom. It has been cut in half. It has been cut in half. I don't know, are we together? You see that it has been cut in half. I think from the one that you have, that I've sent in the group. Let me try to search for it so that when I'm explaining. Okay, so it has been cut in half. So at every face, this atom has got how many? This unit cell has got how many faces? 1, 2, 3, 4, 5, 6. There are 6 faces, right? So at each face there is a half atom. So here there's a half atom even at this face. That face, Kulia, that face, Kulia, at the face below. So I think that's clear from the diagram that you have in the book. We are saying on each face there is an half atom. There is an half atom here, one half atom, half atom. That face that is that side, half atom. Face that is behind, face that is at the bottom is what? Half an atom. So how many atoms does this unit cell have? Yes. They are what? 4. Okay? I'll come back to you. Anyone else? Yes. You think there are 2? Okay? Come back to you. Anyone else? Okay, give me the reason why you're saying there are 4.
I said that half each face, so we have by 6 faces. Then in the corner there are also that the one in
Okay, so she's saying that, okay, before I elaborate what she was saying, where was it? Was you. It was you who said that there are 2. Give us a reason. we've got what? We've got 8 corners, and on each corner we've got 1/8 of an atom. And we also have how many faces? How many faces do we have? We have got 6 faces, and on each face there's half an atom, right? So this will give us what? This will give us 1 plus this will give us what? 3. This gives us 4. Now I believe that you are following. Okay, so this gives us what? 4. Do we understand that? Okay. So this means that the first centered cubic has got how many atoms? It has got 4 atoms. The other thing that you need to determine about the same face centered cubic is you need to determine its volume. Guys, if I just remembered the volumes from my head, trust me, I would have just been writing them. Remember, I just like it that I can't remember them. That's why we are writing them like this. Okay, so let's try to find the volume. We know even for this one that the volume is, I hope now I'm in the footer. We know that the volume is also V is equal to 8 to the power 8 to the power 3. But for this one, we have the center atom like that. We can't say, we know that this distance is A, but we can't say that this distance is 2r. Can someone give me the reason why we can't say that this distance from here to here is 2r? Yes. Because of the space where in between. Yes, this is r and this is r when we end, but there is a gap here. So we can't say that this is 2r. So how are we going to find the volume? We're going to find it like this. Do you agree with me that the distance from here to here is r? Even the distance from here to here is 2r. The distance from here to here is what? R, right? This is A, and this is also what? A. You agree with me, right? Yeah. So if we take this as a triangle, we can say that this is for what? For R, here we've got A, we've got A. We can easily compute what? We can easily find the relationship between A and R. So this is our hypotenuse, these are our sides. Okay. So we can say, using trigonometry, we know that A squared plus A squared should be equal to 4R squared, right? So if we add these, we get 2A squared, this is equal to 4R okay, I can introduce square root here, even here square root to get rid of the square. I'll get A root 2A to be equal to what? 4R, right? So A is equal to 4R over what? Okay, have you all followed me? Okay, so I can rationalize the denominator, and what I'll get will be what? 4 root 2R over what? over 2, right? Guys, when you do this, you get this. So 1, 2. This just simplifies to 2 root 2 r